Hi, I'm Hamza. I'm one of the authors of this paper, which talks about the Tor network. And without further ado, let me just get into it. A bit of a background on the current internet. So, how exactly do you reach a URL right now? Well, if you want to reach a website, say indepthnews.com, you ask a DNS how you reach that from the URL. And it basically returns an IP, which is the endpoint where you want to go to. And later on, you can just send a packet to this particular IP to reach the website you were trying to go to. This packet has your IP written as well if you want the packet to reach you, and that's the source IP. And this is normally fine. You want something back from the website you're trying to reach, but um, there can be a problem in this. If there is someone in the middle who's trying to monitor your packet, which they can pretty easily do just by reading the contents, um, they can tell an adversary about what the destination and source of the packet is. So in this case, for example, they can tell an adversary that, hey, this person was trying to go to 8.8.8.8, which is in-depth news, and the adversary might not want you to go to in-depth news, so they might just show up to where the source IP is and try to stop it. Um, that's where the Tor network comes in. It's designed to protect your anonymity, and it does it using intermediaries. In particular, it adds three nodes: a guard node, a middle node, and an exit node. And the guard node knows where who's sending the packet, but not where it's going. The middle node knows nothing, and the exit node knows where the packet is going, but not who sent it. And the idea is that with these three, you make a unidirectional Tor circuit, which preserves the client anonymity. That's why it's unidirectional. It only preserves the client anonymity. Making the, yeah, this circuit is usually secure unless the guard node is compromised, and in which case you can try to correlate traffic, but yeah, that's just what Tor is right now. Establishing a Tor circuit is also slightly non-trivial. What happens is you talk to a directory authority and you ask, hey, which node should I pick from a large set of volunteer nodes, and it gives you the list of all of the nodes. Then it's your call which ones you want to pick. You choose three at random, and you basically make a unidirectional Tor circuit as a client. Typically, you're more reserved about picking the guard, maybe something which has a higher bandwidth and has more uptime. But this basically protects your um, the client side anonymity. And an adversary can't do anything to you, but what they can do is try to stop the content you're trying to access. So yeah, we want servers and content providers to also have a way to stay anonymous. And Tor also allows for that. They call them onion services. That's where our title also comes from, onions. But what they do is similar to a DNS. The content provider tells a hidden service directory, which is like this abstract data structure, that hey, this is my onion URL, this is my public key, and if anyone wants to talk to me or read my content or whatever, they can meet me at this particular IP address, which is the exit node of a circuit they made. And later on, someone can ask, hey, how do I talk to the onion URL? You get the IP node of the exit, the IP address of the exit node, and then you basically negotiate a circuit. And ultimately, you end up with like these two circuits, two unidirectional circuits, which are connected to each other. And that makes a bidirectional Tor circuit, which has 6 nodes, and it protects both the client anonymity and the content provider anonymity. And DHS there kind of acts like a DNS in all this, but it doesn't know what the IP of the content provider or the client is. And all the traffic goes through these 6 nodes. So that's Tor as is, and this is great. It provides bidirectional anonymity. But there is a problem. And the problem is that if you have a malicious client, if an adversary is trying to figure out where the content provider is, they can just connect to the content provider and make a bunch of different connections. And since the content provider has to stay up, they that the connection will go through. You can send traffic to them, and if coincidentally, for example, the guard node on their side happens to belong to the adversary, it becomes trivial to figure out who is the content provider, what the IP address of the content provider is. You can just send a traffic pattern to that content provider's onion URL, and you'll see it on the other side, and you can correlate them. This is a difficult problem to mitigate. Like, you want to keep the guard node the same. Like you want to not change the guard node as often as the content provider, but at the same time, there's a risk of which guard node you pick. What if you always end up picking the adversary's guard node and so on? It's non-trivial, which is one of the problems we are trying to solve in this. And the the big reason this is a problem is that the malicious client will always have the way to interact with the server, which means they can always try to correlate traffic and so on. Yeah, to summarize, a malicious client can always connect to a server at will, and the server must remain online to provide content. That's a problem. Our solution is to add an intermediary, which we call a vault, and that's what the clients will connect to, not they won't connect to the content provider directly. It's going to look a bit like this. There's bidirectional Tor circuits in the middle. We'll get into this in a bit more detail, how this is established soon, but basically it's somewhere in the middle. It doesn't let you talk directly to the content provider. So if this somehow works, we'll get into how it works. If this somehow works, then the content provider doesn't even need to remain online. They can leave, and the client has no way to connect to the content provider in an ad hoc manner. They just can't initiate a connection. But this does have some requirements. The first is that the vault should be able to prove to the content provider that, hey, I am serving the content you gave me without modification. Secondly, they should be able to prove to the client that they're serving the right content. They're not serving their own content. We don't want the addition of the vault to change the Tor architecture significantly because that's bad. And we don't want the addition of a new actor to create a new attack surface or make de-anonymization easier. These are all the requirements, but if we get all the requirements down, we can have the benefits. We'll start with proof of content to the content provider. And for that, we will use trusted execution environments, which did inspire us to maybe think of this as a title, but we settled on the other one, putting the T in Tor. Yeah, so trusted execution environments. They let you take arbitrary code and run it on someone else's machine. So let's suppose we have a machine that belongs to an unknown entity. We want to be able to trust them to run my arbitrary code. And what does this trust entail? It entails two things. One, they should be able to prove that the code is not modified. Second, they should be able to prove that they can't snoop the program state. So if I have like a password or something that I'm going to enter into the code, they shouldn't just be able to read it from the memory. Trusted execution environments are designed to let you do that. You just send over your arbitrary code to a T-capable device. Intel, for example, has Intel SGX. And they run it inside a fancy thing called an enclave, which is basically a space where the memory is protected by hardware, like the memory protection is hardware enforced. And this means that even the OS and the hypervisor, meaning the person who owns the machine, they can't do anything about it unless they break open the silicon or something, which is very tough. And the second thing that Ts can do is they can provide a signed measurement of all the enclave's contents, like the memory, the code, etc. And this can be very useful because you can then verify if it's exactly the code you sent over. This key is signed using a private key burned into the processor, so there is no way to spoof it. There's no way for the machine owner to access it, for example. And you can just check it with the public key available online, whether this was a right measurement or not. So yeah, we are going to assume Ts work correctly. There's a whole bunch of side channels and work on mitigating those side channels and so on. That's a separate topic, I think. Yeah, so they can prove that the code is unmodified and they can prove that it's running inside an enclave, which means it's private. So yeah, let's talk about our architecture, which we call the Vault architecture. So Vault basically advertises themselves and says, hey, you can go to this Onion URL which they made if you want to reach a vault. And let's say our content provider connects to that Onion URL, which is readchs or .onion. They can upload server code, which can, for example, include a password hash or some other authentication means like a pub key or something. And once they send over the server code, the vault will first run it inside an enclave and then publish the service as something, let's say vlt.onion. And then they'll tell the content provider, hey, I'm running your code. It's running on this Onion URL. Here's the measurement for proof, and you can check it vlt.onion. So the content provider first checks the measurement. Is it fine? If it's fine, it connects to vlt.onion, and using the password hash or the other authentication mean, whatever, it logs into that piece of code and it uploads a bunch of content, and then it leaves. It basically announces, hey, you can reach my content at this other place, which is called vlt.onion. And if a client wants to access the content, they will connect to vlt.onion. And there is no way to connect to the content provider anymore. And this is interesting because now the vault is serving the content, and there is no way for the client to reach the content provider directly, which is what we wanted. We didn't want the client to be able to make a connection directly. This has some interesting consequences which we'll get into later. But yeah, because of these, we basically can prove the content to the server. Proving it to the client is a lot easier because the client just has to trust the content provider. And since the content provider trusts the vault, for them it's just a change in the onion URL which they're visiting. So proving it to the client is not a big deal. This bootstrapping of a vault, all of it just uses the same Tor circuits, 6-hop, exactly the same way. It uses HSTRs in exactly the same way. The only difference is that the content provider might need to publish a self-signed certificate, but they'll do it in the same way as vlt.onion, like they'll publish it along with the onion URL. So it's just a minor extension to your browser. And if you have a malicious vault, well, that's an interesting thing, but we can make a mirror of it with the actual Tor architecture right now. It's not, you're still connected to the vault with a secure bidirectional Tor circuit. And that's also the case when you have a malicious client right now. And even now in Tor, if these connections are super infrequent, then these Tor circuits are considered safe because you need time to correlate traffic and fingerprint and so on. So given this, we believe that the vault at worst is as bad as connecting to a malicious client. And if it's infrequent enough, that's not a problem. And if it's too frequent, you might as well display the content yourself, perhaps. It might even be better because the client could always initiate connections to the content provider, whereas the vault cannot do that. Okay, given this, I believe we have met the requirements for a vault, so we can have the benefits. There is a small thing of the overhead of running it in a vault in an enclave. Like a T has some non-trivial overhead because it's hardware protected memory. But in summation, what we found in our implementation is that because Tor has 6 hops that already have such a high overhead, the running it inside a T is not that bad. The overhead of running it inside a T is not bad compared to the 6 hops. You can look at more details in the paper and for our experiments and so on, but yeah. Moving on, one might wonder why one would even become a vault. Well, one could just volunteer, like the 10,000 or so nodes right now that are volunteering as relays. Or they could have some anonymous crypto payment scheme with zero knowledge, which they might use to be incentivized. Like it's either for ethical or financial reasons. Maybe they just really care about privacy. And this raises some fun questions like, how liable is the vault for the content they provide? In the current architecture, a content provider knows exactly what they're serving. So if an adversary catches up to them, they don't have much of an excuse. But Vault is just running some code inside an enclave. They would have to launch an attack to figure out what the contents are. A Tor, they're just passing content along for all purposes. So are they that different from a Tor node? They are not privy to the content itself. That's something to think about. There are some other interesting thought experiments too. Like imagine a world in which all onions are like hosted in a vault. If, for example, you just decide to host your own content in a vault, which you happen to own as well, then, and can you claim to an adversary that, hey, someone else uploaded this content, I am not the owner? Does that increase your plausible deniability? Does that increase the privacy of vaults or content providers? That's an interesting thing to think about as well. Or some other things, like currently you basically have to trust Google or Amazon with the code they're running. But in this architecture, the vault is not the only one who can verify program integrity. After you've done bootstrapping exactly like before, the content provider can also just say, hey, this is the program I uploaded. it matches a known template. Can you just, yeah, it matches a known template, and then they can leave. And then they're out of the picture for all purposes. And then when a client later connects, they can they can check if the program matches a template they expected, like if it's a safe template without any backdoors, for example, or any way to read your private content. And if they're trusted, they can just upload any confidential data they want. They don't need to rely on the code being trusting that the code is correct. They can check it themselves. And later on, if a vault, for example, decides to say, hey, I will stop running my service, which I'm hosting for someone else, unless you pay me crypto, then clients could even chip in. And this could create vaults which are crowdsourced and trusted. There's some other interesting things to think about, like can we upload content to a single vault and have it duplicate to vaults in some sort of automated manner? You'd have to do some attestation or verification of measurements automatically. Or can we figure out a way to load balance over Tor for all these vaults? That's like part of the future work. But yeah, that's about it. Thank you.